given by Thakur, and over to you.
Thank you. So, first of all, thank you for staying for the last talk of the last session of the last Premier Peer Conference of 2019. I'll be talking today about our experiences with performing precise yet efficient JIT analysis for Java programs. This work was part of my PhD at Pace Lab IIT Madras with my advisor V. Krishna Nandivada, and this was published in ACM Toplas in July. I guess the pointer is not working. Yeah. So let me start by again going over the mechanism, the interesting translation mechanism of Java. So basically, in order to maintain platform independence, we have a static Java compiler which converts Java source code into class files, bytecode basically, which is platform independent, which is then given to a Java virtual machine where the JVM might start interpreting the bytecode, and it may well have multiple compilers which can translate the code just in time to native. So we have different compilers, more work. And we started this work with a question. We keep reading papers on different kinds of precision enhancement techniques, essentially for performing various analysis, context sensitivity, whole program analysis, on-demand analysis, and so on. And we asked ourselves the question, why are these techniques only for static analysis? Why don't we see in JIT analysis? The answer essentially is that the time to perform program analysis during JIT compilation gets added to the execution time of the program, and hence there is a trade-off. The trade-off is more important in JIT compilers compared to static compilers. So if you want to generate highly optimized code by performing a precise analysis, you might end up spending more time in compilation, and hence typical JIT compilers, they adopt the approach of targeting a fast compilation time and then performing fast analysis, let us say intra-procedural instead of inter-procedural, but that may not give you the best optimized code that recent advances may allow. Another approach which probably we thought could be done is, let us perform the analysis statically, let us perform a precise analysis statically, generate the results, let's say that store them in something .res files, take it to the JVM, use the results. Let's say we have a component called as the results adapter, which just uses these results to generate highly optimized code while still keeping the compilation time low. But there is a big problem with such an approach. What if, let us say, the libraries on my source machine are different from the libraries on the target machine, and I performed a whole program analysis assuming a certain version of library? My results may go wrong. No, not acceptable. So if we want to perform such an approach, the analysis has to treat the library calls conservatively, and we again come back to the problem of imprecision. So this was the background. Let me just illustrate these problems with a concrete small analysis called as escape analysis. So in escape analysis, the target is to classify objects into objects that escape, objects that do not escape. So objects that escape in Java, they can escape essentially if I am assigning an object to a global variable or a thread object, or if an object becomes reachable from another already escaping object, then the object escapes. So this is thread escape analysis, and it has several applications like eliminating synchronization if the synchronization is using an object, is taken on an object which does not escape. So a quick example, in this code I have two objects, two objects allocated, one at line 6, another at line 7. And if I represent objects with the line numbers at which they are allocated, I can represent points to information in the following manner. I can say A1 points to 06 because it's allocated at line 6, A2 points to 07, A2 is assigned to global, so global also points to 07, and the escape analysis on this program would say that 06 in this program does not escape the current thread, whereas 07 escapes at line 8. Till line 8 it doesn't escape, but it escapes via the assignment to global at line 8. Now so this is about the C2 compiler of the hotspot JVM, which performs escape analysis, which essentially uses a connection graph kind of a data structure for each method, and then performs reachability over the connection graph and generates escape analysis results. So here I have two synchronization statements at lines 6 and 12, and let us see if we can eliminate those synchronization statements. So at line 6, The synchronized operation is taken on R2, which essentially escapes. So if I generate a connection graph and perform reachability, I would find that R2 points to O5, which is reachable from a global, and hence it escapes. So the synchronization at line 6 cannot be elided by the current C2 compiler's escape analysis. Whereas at line 12, I am taking a lock on the object pointed to by X, which is R1.F, which is essentially an object the R1.F is allocated at line 8, but then R1 is passed to the library method add. And assuming that the add method of the library does not assign the object pointed to by the F field to, let's say, any global variable or any escaping object, synchronization at statement 12 can be removed. But not at line 6, as we have seen. Similarly, let us say I chose the other option which we saw earlier by performing a flow sensitive static analysis. So a flow sensitive static analysis should be able to elide the synchronization at line 6, because the object pointed to by R2 does not escape at line 6, it escapes later at line 7. However, as I said, we have to assume conservative results for the library, and hence I do not know what happens to R1 or R1.F inside the library, and hence the other synchronization statement cannot be elided. So now let us see how can we elide both those locks and more using our approach called as the PYE framework. PYE stands for precise yet efficient. What we do is we add two components for performing analysis. The first one is, let us call it the partial analyzer, and the second one is a fast precise analyzer. And the first one is added to the static Java compiler, the second one is added to the JIT compiler of the JVM. And what do they do? So the partial analyzer, the aim, as I said, is we do not want to assume conservative results if something is passed to the library, but we do not want to ignore the library as well. So what we do is we analyze applications independent of the JDK library. Similarly, we analyze the JDK library independent of the applications, and then we generate static analysis results. So the partial analyzer analyzes the portion of the program which is available to us, let us say only the applications, not the JDK, and then generates something called as partial summaries. In these partial summaries, we encode the dependence. If, let's say, some object is passed to a JDK library, we encode this dependence in the form of a notion of conditional values. We'll see an example soon. So, and then we similarly analyze the libraries independent of the application and generate correspondingly conditional values contained in partial summaries. These partial summaries are stored, again, you can store it with class files in any manner. Let us say we store them for simplicity in something called as .res files. How will these partial summaries look like? In order to explain partial summary, let me first give a model for the traditional summary. So we can say that traditional program analysis, for each element in the domain of the analysis, they give you a value in the lattice of the data flow values of the analysis. So for example, we have seen escape analysis. Escape analysis, for each object in the domain, it might tell you whether it escapes or does not escape. So one of the two values, D or E. But when we generate partial summaries, instead of generating D or an E, we say that we will generate a set of conditional values. So this is like a third value which we will generate here, but it's not a definite answer. We do not know, it's conditional on something. It encodes the dependence, and the thing which has to be encoded in a conditional value is the following. So let us say an object OA is passed to a library method, then a conditional value should encode the information that OA escapes if the corresponding parameter escapes in the library method. This is just a dependence we store here. And a conditional value at a lower level looks like this. It has three elements. The first is a pair which represents another element on which I depend, and V and V prime are simple are values from the original data flow lattice of the analysis. So let us say I have a conditional value tau is equal to ux vv prime in the partial summary for the element E. So what does it mean? It means that I can evaluate this conditional value tau to the value v prime if I know the answer about the element x in method u and if it is v. So if let us say some other object on which I depend, if it escapes, then I escape, or at least this conditional value would give me an E, as simple as that. As we can see, now I am depending on some other methods elements. So if those methods, I am analyzing an application, and if the other method is also an application method, then I can know the status of the corresponding object and I can resolve the escape status, I can evaluate the conditional value. But if it is a library method and I am analyzing the application, then I cannot statically resolve this conditional value. So I have to keep it as it is. Now let us come back to our example. So here we said we want to find out whether we can elide the synchronization operations at lines 6 and 12. And let me just simplify the notation for escape analysis. For escape analysis, if the other object escapes, I do not escape. If the other object does not escape, I do not escape. So let us, instead of 4 tuples, I'll just use u comma x, which gives me the element on which I depend on. So for this program, O4 is basically passed at line 10 to the LST method. It's the first parameter of the add method. So I can generate a conditional value which says if the first parameter P1 of the add method escapes, then O4 will escape, otherwise no. Similarly, O5, the object at line 5 has escaped at line 7, so I can generate simply a conditional value, let me call it theta e. Without any condition, this object escapes, it's an unconditional escape. Similarly, at line 6, here is an optimization which we did. So at line 6, we introduce another abstract object representing the synchronization statement, and at line 6, since the object pointed to by R2 had not escaped, we say that it's theta d. So we can elide this synchronization statement even statically if you want to. And at line 12, we have multiple conditional values because the object pointed to by x or r1.f escapes if the object pointed to by r1 escapes or the one pointed to by r1.f escapes, any of them. So we generate these kind of conditional values, and as the diagram shows, we generate such conditional values and send it to the JVM apart from the simple bytecodes, and where we have the fast precise analyzer, which again has 3 subcomponents. The first component, partial results accumulator, basically reads the relevant partial summaries for the application being executed by the JVM, and in the partial summaries we might have unconditional values. Sometimes you don't need to do anything for them, but there might be dependencies. So in the JIT compiler, the main task is to simplify those or resolve those dependencies in a component called as the summary simplifier. I depend on somebody else, so I should just see what is the escape status, for example, of the other object. And the final step is to switch from using the JIT analysis of the existing JVM. Instead of using those results, I should use the results generated by the summary simplifier. So this is how we can use these results in the JVM. So if I have time, I'll just quickly tell some mathematics behind how do we simplify the conditional value. So we can just say that, as we have seen, a conditional value can be evaluated if I know the final answer for the object on which I depend on. So that is how we simplify, and there can be multiple such conditional values. So we take a meet of all of them by looking up different answers, by looking up the evaluated values of different conditional values, and I can get the final result for any element in the JIT compiler. So equations 1 and 2, if we solve them till a fixed point, we get a final answer from the original data flow lattice for each object in my program. Because and why can't we do this statically for everyone? Because we did not have the evaluated value of u comma x available if u was a library method, which is available in the JVM. So let us complete the example. Here for the object O12, we had 2 conditional values. Similarly, let us analyze, assuming that the add method was as simple as that. Here the first parameter of the add method is just stored to the array, which could be a field in the class array list, and hence the conditional values which I would generate would be like, if the first argument already escaped in the caller of this method, then the object, then OP1, the abstract object represented by the parameter escapes, or if I am storing it into the array field, so if the array field, which is the 0th argument or the field, if it escaped, then this guy also escaped. So we can just solve these conditional values. I depend on you, you depend on me. This is a circular dependence. So here it gets simply cancelled, and we can see that after solving these equations, the synchronization operation at line 12 can also be elided. Why also? Because line 6 I already had a simple unconditional value theta d, which said you can anyway elide this synchronization operation. If this is fine, I'll just move ahead to the evaluation. So we implemented the kind of escape analysis which I discussed. Apart from that, we also implemented one points to analysis which can be used for eliding null checks in the JVM. And as we saw, we had two components, one static analysis, the other for a JIT and the JIT analysis. So we implemented the static component in suit. And one point to note here is that we scaled our static analysis using a clever approach called as LSRV context, which basically gives precision comparable to object sensitive and value context based call site sensitive analysis without taking much time, while taking much lesser time. So we use that approach to scale our static analysis, and we implemented our JIT component in OpenJDK version 7. We evaluated these on several benchmarks from Spec JVM, Decapo, and so on. And we compare, in the next few slides, we compare the results, the precision and the efficiency with the existing analyzers of C2. So this graph is, these are just representative results for the first analysis. So on the y-axis, we have the number of synchronization operations which were elided. And as you can see, the blue bar is the existing escape analyzer of C2. As it generates, the existing analyzer generates connection graphs, performs propagation, but as we can see, it doesn't elide any synchronization operation whatsoever. Whereas we can see that when we use this more precise static analysis results, we can elide several synchronization operations in the JIT compiler. But how much time did we take to do this? This is more interesting. So now we said we do not perform any analysis in the JIT compiler. We just resolve conditions wherever there are conditions. Some places we don't even have conditions. So if in terms of percentages, we take less than 1% of the time taken by the existing escape analyzer, because we are not doing any specific construction now. But the time is negligible because the number of conditional values here were not very high. But as you can see, there is a huge difference. So basically what we get is we get precise analysis results at almost zero cost. And this, even for one analysis out of the tens of analysis performed by the JIT compiler, we saw that it leads to nearly 0.5% improvement in the overall JIT compilation time of the benchmarks. In the paper, we have more details about the other instantiation pace. Similarly, we have several optimizations in the paper for efficiently generating these conditional values and making sure that the overhead we cause for reducing the .res files is as small as possible. And we also have some proofs arguing about the correctness of the approach. To conclude, we can see that PYE solves an important challenge with modern just-in-time compilers, and the proposed approach of partial summaries is a promising idea to finally be able to utilize the recent advances in program analysis and get precise analysis results during JIT compilation without affecting the compilation time much. And one interesting thing here is that we could even perform complex optimizations now at lower levels of compilation. Since we do not affect the JIT compilation time much, let's say C1 does not perform any synchronization elimination correctly. Now I have the results of escape analysis already available with me. I can perform that in C1 as well if I just have an optimizer implemented, for example. We can perform it in the interpreter as well. And yes, the techniques proposed are not specific to Java. They are as such general enough. We can extend them for C# or any other language where we have the opportunity to analyze statically before running the program in the JIT compiler. Thank you.
Thank you. Really nice work.
Thank you.
What I was wondering, I have actually two questions, but I'll let someone else ask a question after the first. Once you have these values that are dependent on summaries from the libraries,
right?
Do these make your lattice in your static analysis much larger than the lattice that you start with?
So if I say that my dependence is only on different elements, so I'm just storing, so the lattice earlier has, let's say, n values, I'm just having an n plus 1th value which lies in between. And now the number of values, the number of values which we can obtain is, depends on the analysis now. So if I want to generate, let's say, points to results in this form, then yes, if I want to say that I point to O1 if somebody else points to O1, if I point to O2 if somebody else points to O2. So it depends on basically how do you generate these condition values. Instead, maybe I could say I point to whatever somebody else points to. So then I would not add so many condition values. I hope I answered your question.
All right. Thank you. Yes.
Thank you very much for sharing this. I find it very interesting, specifically because to me it looks an awful lot similar to the general theory of partial evaluation. So in this case, it's like, okay, well, I have a global analyzer, but I only have partial input to it. And the problem is that if I do the whole analysis only when all the input becomes available, which is at runtime, I'm too slow. So I'm only compiling the parts that depend on things that I already know. And on runtime. So how much do you think there is a potential for cross-pollination of ideas between the general partial evaluation and what you do? Can we take, can the partial evaluation theory can take ideas from your analyzer, or can your analyzer take more, because this is a very concrete example, but I guess this is just an example of what your framework can do. So how much of the general partial evaluation ideas are applicable in your context?
Good question. So I'm not too well versed with the theory which is existent in partial evaluation, but yes, so this is just a way to perform partial analysis, and as such, let us say you want to use an existing idea to generate different kinds of conditional values, different kinds of dependencies. You can perform this, you can use such an idea to not only perform program analysis but maybe something else. So I guess, yeah, we can use the existing theory from partial analysis. And one thing I would like to add here about what we do here is we guarantee that anything which is available, which can be resolved statically, we do it statically. So there is nothing which could be resolved statically but is left for the runtime. So that gives another boost over here. But yeah, it would be interesting to look at even other frameworks, and I guess we can for sure use a cross pollination of the ideas. Yes, thank you.
Okay, so you showed that your overhead during JIT compilation is much lower because you've basically already computed everything.
Right.
What's the overhead of the compile time?
What's the overhead?
The overhead of the static compile time. So the analysis that you do beforehand.
Right. So I have it in my backup. Yes. So this is for the escape analysis, and these are the numbers. On the left hand, we have time in seconds. So as you can see, typically with the size of the benchmark, the time increases. But there are two things which give you such a nice graph of just a few seconds of time for such big benchmarks. So one thing is, as I mentioned, we scale our static analysis significantly using the idea of LSRV context, which I would maybe discuss with you offline. And another thing to note here is that we are getting the results of a whole program analysis, but while performing the static analysis, we are not going inside the libraries at all. So we are just scanning the application. So which gives a very significant boost to the time we spend in static analysis. So as you can see from this graph, the time spent in static compilation is quite reasonable, I would argue.
Okay, thank you.
Thanks.
Any final question, anyone? Yes, I see a question here. Sorry for this.
Not so much a question as a remark. There's at eCoop this summer there was the eventually sound compilation static analysis by Alex Aiken's group, which is very similar to your technique. Because effectively what you're doing technically is you are analyzing modularly the program versus the library, and then you create those, let's say, conditional summaries for the library that say, if this is alias with that, then propagate that information when you find out what the library really is. And it's very much the same idea. So it's very interesting that there were two recent pieces of work that came up with pretty much the same idea, which is very nice.
Oh, great. I'll go over the paper. Thanks.
Very good. Thank you again.
Thanks.